Hello and welcome to another episode of Risky Business. Last time we were having some confusion over these this whole concept of pulse width modulation, and so afterwards I found a video which we'll go over. And then there's this nice write-up that this person has as well. And so we're going to go over that. And then Hossein had some useful messages as well. Let me switch to Chrome here. Because Pale Moon can't play the video. Okay, so Hossein says, just think of the average of the pulse as the area covered by the pulses. So say we have a pulse that is 3.3 volts for 500 milliseconds and 0 volts for 500 milliseconds, duty cycle of 50%. The average voltage would be 0 times 500 plus 3.3 times 500 divided by the total amount of time there, the 10,000 milliseconds. And then that gives you 1.65 or 1,000 milliseconds. And so that makes sense. And then he has this video here that I want to show. So I don't know, Hossein, if you can tell me, is this like an oscilloscope? I don't know how you even pronounce that. Like, what kind of hardware is this? I'm interested to know. The video is going to be a little bit cut off. Let me see if I can temporarily turn off my thing. Let's see, which one is the... There we go. All right, so this is just a short little clip here. And I'm not sure what exactly this piece of hardware is, if it's an oscilloscope or what. But you can see here Hossein is showing he connected this thing up to the pin for the green channel. And okay. I'm definitely going to take a look at that piece of hardware later. But yeah, you can see here the actual pulse that it's doing. So that's a very cool little thing there. And let me turn back on my my overlay. All right. And another thing you can see on my Twitter there, I'm glad I went on Twitter because I almost forgot to point this out. I have received my pre-order of the risc-v edition of Computer Organization and Design. So that's very exciting. It comes with the first page. There's a little tear out green card for you. So that's a nice inclusion in the book. And then a lot of interesting stuff in this book, of course. I'm thinking we might want to do kind of like a book club type of thing on the series. Maybe like once or twice a day, or once or twice a week. We could have an episode that focuses on content in a book. I think that might be a fun thing to do. Especially since I have this book now, I think it would be very fitting. I actually have here, I already owned a copy of this book, the previous edition, which I believe was using MIPS instead of risc-v. This is a used copy, So it didn't come with the green card. And I only read like maybe one or two chapters out of this one, and I never got around to reading the rest of it. But now that I have this version here, I'm definitely going to be motivated to read the entire book. It's not that it's bad content, it's just that I didn't get around to it, you know. I've got tons of books lying around that I never get around to reading, but I want to. But anyway, let's get back to PWM. So I think I'm going to play this video for you guys. It's like an 8-minute video, and I might set it on like 2x speed, so it's 4 minutes. All right, now.
LEDs. In this tutorial, we will cover the basic principles behind PWM and how it can be used for LED brightness control, including fading out LEDs rather than just turning them on and off. To control the brightness of an LED, you can vary the power which is sent to the LED. The more power the LED receives, the brighter it is, the less power the dimmer it is. However, microcontrollers are digital, meaning they only have two power states, on and off. PWM provides the ability to simulate varying levels of power by oscillating the output from the microcontroller. If over a short duration of time we turn the LED on for 50% and off for 50%, the LED will appear half as bright, since the total light output over the time duration is only half as much as if it was 100% on. The pulsing width is the important factor here. By varying or modulating the pulsing width, we can effectively control the light output from the LED, hence the term PWM or pulse width modulation. When using PWM, it's important to consider how slowly we can flash the LED.
Let's set it on like 1.25. So this guy shows PWM stuff.
Them on and off. To control the brightness of an LED, you can vary the power which is sent to the LED. The more power the LED receives, the brighter it is. The less power the dimmer it is. However, microcontrollers are digital, meaning they only have two power states, on and off. PWM provides the ability to simulate varying levels of power by oscillating the output from the microcontroller. If over a short duration of time we turn the LED on for 50% and off for 50%, the LED will appear half as bright.
I want to pause it right here because this is one thing that I think was one of the issues that I was having in understanding this is the concept of the duty cycle. So I think he really does a great explanation of this and like visualization of this. So let me turn off the overlay stuff again. There we go.
Since the total light output over the time duration is only half as much as if it was 100% on. The pulsing width is the important factor here. By varying or modulating the pulsing width, we can effectively control the light output from the LED, hence the term PWM or pulse width modulation. When using PWM, it's important to consider how slowly we can flash the LED so the viewer does not see the oscillation. The eye's inability to see rapid oscillations of light is caused by our eye's persistence of vision, which means we see the light is on for a short duration even after it's been turned off.
So that's the other thing that I was wondering about yesterday is when I thought about this, the first thing that jumped to my mind was like literally flickering the LED on and off. And it turns out that's actually exactly how it works. Is the human eye can only perceive, you know, motion at a certain like frame rate, and so if you're flickering it faster than that, we don't perceive the flickering, even though it's actually turning on and off really fast. And so what happens is like if it's on for, you know, 50% of the time and it's off for 50% of the time, then we end up seeing like the light is half as bright. This is a concept that I was kind of familiar with before this because like I used to do programming of graphing calculators because they were required in high school, and that's how one of the main things that got me into programming in the first place. And people who make games for those graphing calculators, I think they have color screens these days, but back when I was in high school, they had black and white monochrome displays. And in order to get grayscale, they would do this trick where they flicker the pixels really fast. And it wasn't quite fast enough that you didn't totally see the flickering. You could kind of tell. But you'd get some pretty nice grayscale effects doing that. And so I was a little bit familiar with this, but yeah, that's actually how the LED works. And that's something that I find really fascinating because, like, in this studying that we're doing of the Hi-5 one, we've actually gotten to the point where we're thinking about biology of the human eye, you know, of what it is capable of. So that's really interesting. But anyway, let's continue the video.
This technique is how televisions display a moving picture which is actually made up of a number of different still frames displayed one after another. The minimum speed of an oscillating LED which can be seen by the human eye varies from person to person. However, for the purpose of this tutorial, we will use a minimum speed of 50 Hz, or 50 times a second, which is the same speed as used by European televisions. When using PWM, there are certain terms which you will come across again and again. The most important is duty cycle. The duty cycle refers to the total amount of time a pulse is on over the duration of the whole cycle, so at 50% brightness the duty cycle of the LED is 50%. The cycle itself is measured, usually, in Hertz, which gives us the cycles per second. So at 50...
Okay, so this is the thing that really clarifies it for me, is we see here we're talking about, we're targeting 50 Hertz in this example. And so if you do the math, you get this, this 20,000 here. And then you see, like, here's one cycle. And then the duty cycle over that, we break it up into units.
50 Hz, our cycle is 1 second divided by 50 cycles, which is 0.02 seconds per cycle. Since we are using such small time measurements, it's more useful to use microseconds. There are a million microseconds in a second. This gives us a cycle duration of 20,000 microseconds, which is 50 cycles per second, or 50 Hz. During the 20,000 microseconds, we have to turn the LED either on or off depending on the required duty cycle. So for example, a 75% duty cycle requires the...
So here you see he's drawn in this this diagram he has here, he's broken it up into these discrete units, and then you see here he's saying like 75% of the total. So like here is, from here to here is the total, and so this much of it is on for 75%. And so we really, this is the other thing that kind of threw me off, I guess, is we don't actually need to think about the waveform that we can create with PWM. We can use PWM to represent these analog waveforms, right? Like a sine wave. But we really, for our purposes, what we're doing here with controlling an LED, we don't even need to think about waves. We just need to think about what they're showing right here with these pulses, where how much it's on directly affects the brightness that we're getting. And so in this example, we're only talking about brightness, so a single channel, but we're doing this on the Hi-5 one on 3 different channels. Each one is a different color that it produces. And so by blending those, we can get different colors. But the concept, this concept applies to one channel, and then you're doing it on 3 different channels. So that makes a lot of sense.
To be on for 15,000 microseconds and then off for 5,000 microseconds. The accuracy with which we can control the duty cycle is known as the PWM resolution. The higher our PWM resolution is, the more levels of brightness we can display. However, since the duty cycle is fixed at 50 Hz, more resolution requires finer timing from the microcontroller. The faster the microcontroller, the smaller durations it can time. Another limiting factor is the code execution. The microcontroller must not only time the interrupt which causes the pulse generation, but also run the code which controls the LED output, which must complete before the next interrupt is called. In addition, you probably want your microcontroller to be performing tasks other than LED PWM brightness control, so there has to be some spare execution time between interrupts to do all of the other more general processing tasks. With PWM control of LEDs, the primary advantage of higher resolutions is that it results in a smaller difference between brightness levels from the LED. For example, if our cycle is 20,000 microseconds, and our resolution is only 10,000 microseconds, the difference between on and the lowest possible brightness will be 50% of the total possible brightness from the LED. At a resolution of 2,000 microseconds, the difference would be 10%, and so on. The higher the resolution, the more timing accuracy and processing overhead. This animation shows a PWM simulation. The cycle time is 20,000 microseconds or 50 Hz, and the resolution is 1,000 microseconds, giving us 20 levels of output. For your application, the required resolution and overall cycle may vary. Simple displays require very little precision control, and sometimes a little flickering is not the end of the world. For more advanced displays, the ability to control the levels of brightness might be more critical. For example, the issue of mixing colors using an RGB LED. The trade-off is simple. More control and accuracy requires more and more microcontroller resources. Now let's look at a more practical example using the microchip PIC18F4550 microcontroller. In this example, the PIC is running at a clock speed of 48 MHz.
So,
this means the crystal oscillates 48 million times.
An example using some other microcontroller, which we don't really care about because we're doing risc-v, which is much more exciting. But I'll play the rest of the video anyway.
A second. The PIC requires 4 clock pulses for each operation, meaning it can effectively process 12 million instructions per second. This processing speed is important since we will need to use a timer on board the chip to time the interrupt we need for producing the PWM output. If the processor cycle rate is 12 million cycles a second, this means 1 microsecond of time passes for every 12 processor cycles, so 1,000 microseconds is equivalent to 12,000 processor cycles. This is important because with a 1-to-1 timer prescaler, the PIC's timer updates once every processor cycle. The timer's prescaler slows down the rate at which the timer's counter updates. If we use an 8-bit timer, the maximum amount the timer can measure is 256 counts. Therefore, we have to pick a prescaler value which allows us to time 12,000 processor cycles in less than 256 timer counts. If we use a 1-to-64 prescaler, we will require 187.5 timer ticks to measure 1,000 microseconds. Since we can't measure a half, we simply round this value down to 187. The timer is then set to 255 minus 187, which gives us 68, and then it's started. When the timer overflows, it will have counted the required 187 counts, at which point an interrupt will be generated. The interrupt must reset the timer when it's finished, and the cycle starts again. Once the timer is configured and running, we need some interrupt code to decide if the LED should be on or off for this interrupt. Since we have 20 possible brightness levels, and therefore 20 steps of resolution in our PWM generation, we can simply use a counter which counts from 0 to 19 and is updated once every interrupt. If the brightness of the LED is represented using a number from 0 to 19, we simply have to check if the PWM counter is higher or lower than the brightness number to see if the LED should be on or off. You can see the result of this here where the LED is being cycled through the possible brightness levels. Since we know the cycle duration of the interrupt, we can also use this to provide fading effects on the LED. To do this, we have to store 2 values for the LED brightness, one to store the actual display brightness and another to store the target brightness for the LED. For fading the LED off, we want to decrement the actual brightness level, one step at a time until it equals our target brightness. Since there are only 20 levels of brightness, we cannot simply subtract a level on each interrupt call, since the interrupt call is too fast for the fade to be perceived by the viewer. 20 calls would only consume 20,000 microseconds, which is way too fast to see. Instead, we keep another counter which counts the number of interrupt calls which should occur in between decrementing the actual fade level. Since we know the interrupt is called every 1,000 microseconds, it's pretty straightforward to work out how many interrupts we should count to get the desired fading rate. For example, if we want to fade from a brightness level of 19 to 0 in 0.5 seconds, we simply divide the required time in microseconds by the interrupt time of 1,000 microseconds and then by the number of levels. You can see this in the video where the LED is being turned on and then allowed to fade. Whilst it's perfectly possible to get PWM controls to work with LEDs using pure guesswork, calculating the desired optimum values makes more efficient use of the available processor resources, allowing you to both do more with the microcontroller and also control more LEDs simultaneously from the same chip. The same technique shown here for LEDs can also be used to control motors, analog meter displays, incandescent light bulbs, etc. You can find out more details about this guide and some example PIC18F4550 firmware on my website.
Alright, so I thought that was a very helpful video, and I want to take some notes from it. And so rather than taking notes from the video, I have the blog post this guy's made, which is linked in the description of that video. And for anyone watching that wants to find that particular video, I posted it on my Twitter. You can find it right here. So there's the video, and then we're going to be taking a few notes. So really the thing we care about, let me turn on the overlay again. All right, so really the thing we care about here is kind of like the duty cycle is really based on the FPS that we're targeting, right? Like it's really about the hertz. So that's the main thing. And then the other thing that we care about is this PWM resolution, as they call it, which is the cycles between a single duty cycle. And so those are going to really be determined by the physics of the device we have, I guess. It's really based on how fast we run and, what we need to do. So we should be able to figure those values out from first principles. But let me fire up Milton here. So I want to take a few notes about PWM. So let's just go over here, I guess. All right, so first of all, let's copy this diagram down. So I'm going to put it into grid mode and draw some lines here. So this value up here is 1. This value down here is 0. And then the x-axis would just be like time. So they list it in microseconds. So I'll do the same here. All right, so the idea here is if we have a 50 hertz target, then the idea there is that is so many cycles a second. So 50 cycles per second would be what 50 hertz is. And then we're saying there's this many microseconds in a second. So that's what, a million? And so we're saying once one cycle in the 50 hertz is that many microseconds. How do you draw a mu? Okay, it's like a line and then a U, basically. So it's that many microseconds per 1 hertz, I guess. So I'm going to say hertz instead of cycle to be more clear. And then we're going to say, so we have 50 hertz. So if we divide that by 50, that gives us the total number of microseconds in a duty cycle. So that number is 20,000. So this, the duty cycle we can think of as being a single cycle of the wave. So like 1 pulse. And then we're going to draw out the x-axis a little bit more. So they go from 0 to 40,000. So we're going to just like eyeball halfway and say this is 20,000 right here. So I'll just dot it. So there is the duty cycle. So now, how many notches did I actually draw? $14. So let's just say like 7. This would be halfway. So, let me put 1 further down. So we're going to say 1 is like right here. So this would give us a wave like this, and this is on 50% of the time. So we get 50% brightness. So this is the real concept of PWM that we care about. We don't actually care about representing a wave for what we're doing. Obviously, it's important for other things, but as far as we're concerned, we only care about the pulse wave, and it kind of directly represents what we want here. Also, I see I'm dropping some frames, so I apologize if I am not able to stream right now. My internet, I'm kind of at the whim of my ISP, so. All right, so OBS crashed. So I'm going to continue streaming like normal, and I'll edit these videos together and post it as a normal episode. All right, so let's get back to it. So this is what we care about, and now the things we care about here are the resolution of like how many ticks are in the duty cycle. So here I've drawn like 14 different ticks on this. So that would be like a PWM resolution of 14 units, right? And so the values we want to know would be the number of the hertz that we're targeting, because that's going to determine our duty cycle. And then we also want to know the PWM resolution. And I should write something on here to show what the PWM resolution is. So I'll put it back into the normal note mode. So this is how many, I'm going to say discrete units we have within a duty cycle. Which is the number of ticks on the x-axis. All right. And it seems that the stream is healthy now. I guess my connection just blinked out for a second. Hopefully it stays stable. So let's see if they have anything else interesting about this that we want to note down. So one thing is in their example with this this PIC18F4550 microcontroller, the way they determine the values is they take the 48 megahertz that the chip is running at, which is 48,000 cycles per second. And they note that it takes 4 ticks of the clock to process a single instruction. So every instruction is 4 cycles of this 48 megahertz clock. And so they use that to determine that the smallest amount of time that they can deal with is this value here. Then they convert that to microseconds. And then they also point out that they're using an 8-bit timer. So, I mean, we're going to be using like a 32-bit timer, right? And we can run at like 256 megahertz or whatever. So we obviously have a lot more computational power at our disposal, but we also are messing with 3 different channels, not just one. So but yeah, anyway, I think that's pretty much everything we want to take notes of from this content. So shout outs to Simon Inns for this this video and write-up. It was very helpful to us. Now, getting back to the actual code that we're looking at. Or I guess we're reading this PWM chapter, aren't we? I don't think we read all this. So let's continue reading this, I guess. So here's the code that we were looking at. So this is the LED fade demo that we're looking at right now. And you can see they're talking about a period of approximately 244 hertz. And then do we have demo GPIO open too? And no, it looks like we just have the LED fade demo open. But anyway, let's focus on the documentation for now. So how much time do we have left today? I think we can go for like another 25 minutes. So I think we read the PWM overview again already, but let's go through it again now that we understand PWM better. So we have a PWM peripheral. So we maybe don't care so much about like the main clock rate of the chip, because this is kind of dedicated hardware for PWM. So we have 4 independent PWM comparators. Custom configurations with NCMP comparators are available on request. The PWM block can generate multiple types of waveform on GPIO output pins, so that's interesting. So it's hard-coded to be able to generate different waveform types, I take it. And can also be used to generate several forms of internal timer interrupt. The comparator results are captured in the PWM compare XIP flops and then fed to the PLIC as potential interrupt sources. The PWM compare XIP outputs are further processed by an output ganging stage before being fed to the GPIOs. The PWM unit can be provided in different comparator precisions up to 16 bits, with the version described here having the full 16 bits. To support clock scaling, the PWM count register is 15 bits wider than the comparator precision compare with. So we're talking about 16 bits then? Or no, the counter is 32 bits. So PWM count register. The PWM unit is based around a counter held in PWM count. The counter can read or be read or written over the tile link bus. That's another thing that we've been skating around. We haven't looked into the tile link bus and what all that involves. It doesn't really matter to us in terms of programming, but it is an interesting hardware detail that we'll want to look at some point, I think. So the PWM count register is 15 plus compare with bits wide. So if we have 16 bits, which I presume we do on the Hi-Five 1, we'll have to check, I guess, but I assume compare with on the Hi-Five 1 is going to be 16 bits. So the counter is held in PWM count 0 to 30, and bit 31 of PWM count returns a 0 when read. So it's 31 bits then in a 32-bit register that we're using for our counter. So that potentially gives us quite a high resolution then. When used for PWM generation, the counter is normally incremented at a fixed rate, then reset to 0 at the end of every PWM cycle. The PWM counter is either reset when the scaled counter PWMs reaches the value in PWM compare 0, or is simply allowed to wrap around to 0. So we can set it up to wrap. So we can, basically this is what allows us to control the resolution. We can set it to count to a certain value within the total supported range. So we don't necessarily need to, or perhaps even want to, use the highest precision that it's capable of. We can use a lower precision. So that's good to know, and we do that using the PWM compare 0 register. So it says the counter can also be used in one-shot mode, where it disables counting after the first reset. Okay, so you can have it so when you hit the reset button on the Hi-Fi 1, once your code starts executing, it'll run a single cycle of the counter, and then rather than counting again after it wraps or hits the PWM compare, it would just stop counting. So I don't know exactly when we would want to use that type of behavior, but it's good to know about at least. We see a diagram here of the PWM peripheral, a schematic, which again, I'm not spending time really looking at the schematics since I'm not really a hardware guy. But we have the PWM Configuration Register here, PWM CFG. So the PWM scale is bits 0 to 3, 4 to 7 is reserved. There's a PWM sticky, 0 compare, de-glitch, reserved, enable always, I assume the EN always is. Enable one shot. Okay, so this is for the one shot mode. Then there's a couple reserved bits. Sorry about that. OBS crashed again. Alright, so let's continue looking here. So we have a compare 0 center, a compare 1 center, compare 2 center, compare 3 center. So I don't know what these exactly are for. 20 to 23 is reserved. 0 gang, 1 gang, 2 gang, 3 gang, compare 0 IP, then there's a 1 IP, a 2 IP, and a 3 IP. So the PWM config register contains various control and status information regarding the PWM peripheral, as shown in figure 15.2. The PWM EN bits control the conditions under when the PWM count is incremented. The counter increments by 1 each cycle only if any of the enabled conditions are true. Okay, so like that makes sense for the one shot. There's also always. Let's see what else we have for enable. So I think it's only those two different flags. There is the one shot and the always. Okay. So the PWM enable always bit is set. The PWM counter increments continuously. When one shot is set, the counter can increment, but PWM enable one shot is reset to 0 once the counter resets, disabling further counting, unless PWM enable always is set. Okay, so the idea is if you want to do a one shot, you set always to 0 and one shot to 1. And then one shot will get set to 0 when it's done. But you can also override that by setting enable always to on. And you would need that set if you just want to count in general, as in not using one shot. So the PWM one-shot bit provides a way for software to generate a single PWM cycle, then stop. Software can set the one-shot again at any time to replay the one-shot waveform. The enable bits are reset at wake up reset, which disables the counter and saves power. That's a good idea. So when we want to use the counter, we need to make sure we enable the enable always bits. So I imagine that's happening in this code, and indeed it is. You see it right here. So we do PWM1 reg. I don't think we've taken a look at that macro yet, but presumably it works like the GPIO macro, and it's just getting us the PWM config register, which I imagine is like memory mapped, and so this like adds a base address, that type of thing. So we set it to 0 just to make sure everything is at a state that we know. And then we're setting the config register to have the enable always bit set, and then we're also setting compare to center. So that's the one I don't know about yet, but we know why we're setting this one, so that much makes sense. And we also make sure the count is set at 0 to start at, apparently. Okay. Okay, so this is exactly what I was thinking. So you see there's this there's a PWM peripheral base address, and this memory map here shows the offsets relative to the base address. So this macro here, without even looking at it, we can imagine exactly what it's doing. Right, it works the exact same way as the GPIO macro. The difference is that it's adding the PWM peripheral base address and the offset. So PWM CFG is going to be defined to be 0x00, for example, where count is 0x08, which is this one right here. Right, and then so it adds those, and then it dereferences the pointer. And then, so we're using that to set these bits here. That makes sense. And, like we can even see, we saw this map of the config register, so we know exactly what value to expect. Like this is going to be, enable always is bit 12. So this value is going to be 1 shifted left 12. And then the compare to center is going to be 1 shifted left 18. So it's ORing 1 shifted left 12 and 1 shifted left 18, and setting that with this config register here. So that makes perfect sense what's going on there. So the 4-bit PWM scale field scales the PWM counter value before feeding it to the PWM comparators. The value in PWM scale is the bit position within the PWM count register of the start of a compare with bit PWMS field. A value of 0 in PWM scale indicates no scaling, and PWMS would then be equal to the low compare with bits of PWM count. Okay, so we can scale the PWM counter when working with the comparators. So why would we do that? Is like maybe the PWM comparators. Oh yeah, that makes sense. The comparators we saw up here, they were talking about how the comparator width is like 16 bits. So we've got a 32-bit counter, or 31 bits, I guess technically, but like it's a 32-bit register, but it's only able to count 31 of those. But because the compare registers are only 16 bits, we need to be able to scale the value down. So that makes sense why we'd have those that scale field. So the value in PWM scale is the bit position within the PWM count register of the start of a compare with bit PWMS field. 0 indicates no scaling. 15, which is the maximum value, corresponds to dividing the clock rate by 2 to the 15th. So for an input bus clock of 16 megahertz, the LSB of PWMS will increment at 488.3 hertz. The value of PWMS is memory mapped and can be read as a single compare with bit value over the tile link bus. The PWM zero compare bit, if set, causes the PWM count to be automatically reset to 0 one cycle after the PWMS counter value matches the compare value in PWM compare 0. This is normally used to set the period of the PWM cycle. This feature can also be used to implement periodic counter interrupts, where the period is independent of interrupt service time. Okay, I don't think I totally follow that. The 0 compare bit. It says if set, it causes the counter to automatically reset to 0 one cycle after the PWMS counter value. So, I mean, PWMS counter is the scaled value, matches the compare value in PWM compare 0. I thought it did that without a special bit. Yeah, I'm not understanding why we have a special bit for that. Like, it says the counter is normally incremented at a fixed rate and then reset to 0 at the end of every PWM cycle. It's either reset when the scaled counter reaches the value in the compare register, or is simply allowed to wrap around to 0. So what happens if you don't have the PWM zerocmp bit set? It just doesn't reset, apparently. So it would still reset if we're not using the scaled value. If we're not actually scaling it, when it overflows, it'll still reset to 0. But apparently you need this bit set to clear out the register when the scaled version passes the value in the compare register. So, I mean, in this fade demo, we're not doing anything like that, as far as I can tell. I'm sure we'll learn more about this at some point and get a firmer understanding of it, though. And we are out of time for today, so we'll have to continue tomorrow. I apologize that OBS crashed a few times, and a little bit of internet issues this episode, but I'll just concatenate the videos together and upload it as usual. But thank you for those who tuned in anyway. And thank you to everyone who watches on the YouTube archive, which is available at risky.tv. And you can follow me at HMN_risky on Twitter to get updates about the series. So I will see you next time, and stay risky, everyone.